Recent studies using advanced high-resolution 3D synchrotron imaging confirmed that anatomical structures important for cochlear stimulation extend deeper into the cochlea than some experts previously thought. Stimulating more of the cochlea is important for cochlear implant users because longer electrode arrays are associated with better speech perception, according to the majority of studies on the topic. Synchrotron imaging has also shown that even in the smallest cochlea, the scala tympani can accommodate Med-L flex electrode arrays up to 2 full turns. By covering the entire cochlea and making use of its full potential, our electrodes can also provide more natural hearing by stimulating each tone at the right place in the cochlea. Med-L electrode arrays are the only electrodes that can reach beyond 1.5 turns in the cochlea to stimulate the low frequencies at their natural tonotopic place in the cochlea. This allows Med-L cochlear implant users to hear the deeper bass tones in music. With improved place pitch match and better sound perception, you can give your patients the closest to natural hearing, more natural music enjoyment, and better hearing in everyday life.
Battery of tests that we use for validation. As you can see, one test alone is not sufficient to determine benefit from device, and that each test represents an important aspect of access to sound in general. So each test is a piece of a puzzle to have an overall picture of what the CI user is getting out of their hearing implant. Next slide, thanks. Now, it is important to remember that the dynamic range of electrical hearing is much more narrower than that of normal hearing, and compression is required to allow the user to access the wide dynamic range of everyday sounds. Med-L has 3 stages of compression happening in our system, and the first step is actually AGC, or automatic gain control. Now, AGC acts similar to a hearing aid, wherein low-level sounds are boosted with higher gain, and low gain is applied at higher sound levels. One way of conceptualizing the action of the AGC is to picture it as a sound level window that moves the level range up and down to best focus on the current overall level in the environment. Traditional AGCs can compress speech signals well, but what happens if there is a sudden transient sound present along with the speech? What the system does is apply a dual loop design to allow compression of speech, but also respond well to transient sounds. So these parameters mimic compression process in a normal hearing, and additionally provide a relatively good match for compression characteristic for bimodal users. Now, the next stage of compression is map law. Map law is essentially electrical compression that handles the loudness growth function in our cochlear implant system. Essentially, this acts on the output of the AGC, compensating for the differences in response between electrical and natural hearing. So it helps the CI user hear a more natural change in loudness as the external sound increases in level. The default levels are generally fine for most of our patients, and we typically look at this parameter if we are suspecting that access to soft sounds are limited. Then last but not the least, we have the electrical dynamic range, the thresholds and the MCL. So this is actually what is set during a mapping session. We define this as the range between the thresholds, which is the THRs, or the highest undetectable stimulus level, and the MCLs, which is maximum comfortable stimulus level. Now, for Med-L, the MCL is the most critical measured parameter for our system, particularly for loudness cues. We know that if you get the levels roughly right, it can result to good performance, but an accurate measure can lead to better performance. And thresholds, for us, it's perfectly fine to leave it locked at 8%. Next slide, please. For Med-L, we aim to make the input dynamic range as wide as possible, and there's a couple of practical reasons for this. First is that we would like to be as close as possible to how normal hearing is. And second, it provides cues to sound level changes even at high input levels. We also would like to avoid too much compression of mid-level sounds. And as we all know, this is where generally speech is. So our input output function results in a target of around 30 dB NHL to 100 dB NHL dynamic range. Quiet sound detection is important, but it must be balanced against performance in everyday environment. Next slide, please. So sound field testing is a useful tool to assess ability to hear pure tones, particularly in cochlear implants, and we often use it as a measure to track progress. But it doesn't necessarily mean that lower sound field thresholds indicates better performance. So to expand on that remark, we rarely listen to pure tones in our daily life. I guess one practical pure tone input might be an alarm, for example, but this type of sound is not required to listen to at a soft level. So generally, they're actually louder. For a CI user, it can take at least 3 months to get near complete stimulation levels due to the physiologic changes in the cochlea brought on by the electrical stimulation. And for children, we may actually need to increase the levels slowly. So what we propose is to always consider a form of speech testing along with your sound field thresholds to validate CI performance. Next slide, please. For Medell, we expect sound field thresholds of about 25 to 35 dB across all frequencies in a well-fitted experienced user. So the typical limitation of speaker noise floor is approximately 20 to 30 dB. If you are in an anechoic chamber, you can potentially go down to 20 dB, but in a regular clinical setting, a more realistic level is around 30 dB. So the processors are designed on purpose to have this level of sensitivity. On the default settings, our input dynamic range is around 65 dB. So if a 30 dB is detectable, we would expect the user to receive loudness cues for level changes right up to 100 dB. And your 3-to-1 compression would start at around 50, 55 dB. This may be particularly important for noisy situations where people naturally raise their voice levels. If we made a 20 dB sound detectable, there would be no loudness cues above 90 dB, and your 3-to-1 compression would start at 40, 45, probably reducing level cues in everyday speech. So if you remember in the previous slide, we aim for a wide input dynamic range, and that's mainly to mimic normal hearing and provide an accurate perception of sound level changes. Next slide, please. So as a summary, we cannot rely on sound field thresholds alone as a means to evaluate a map. We can achieve good sound field thresholds, but keep in mind that this can result in an oversensitive system, picking up low-level background noise and making internal system noise audible. So we always recommend to, with your map evaluations, you should always include some form of speech testing. And the easiest and most accessible form of that is the Ling sounds. Now, I'll hand you back over to Rebecca.
Terrific explanation, Diana. I really enjoyed that. I did have a moment of concern though, because actually I couldn't hear your shh. Did you hear my shh just then?
I can hear your shh, but you know what? I'm wearing noise canceling microphones. So I wonder if the microphone actually tried to cancel the shh, because it's just
well, you know what? That's a lot better than the conclusion I leapt to, which was age-related hearing loss. Maybe we can get a bit of participation from the audience, and they could give us a little reaction. Thumb up if you heard Diana's shh, or is it just me? Donna, can you see the participants there and give us a clue? How about you, Eros? Did you hear Diana's shh? You did. Oh my goodness, it must be my hearing
Okay.
loss. Oh, this is very bad news for me, Diana. I'll be booking an appointment in the next week. Oh, JC also heard Diana's. Shh, maybe it's my hearing technology. Okay. It's a great functional example of how now I'm really concerned. I don't know how I'm going to get through the rest of the presentation worrying about my high frequency hearing loss. But let's go ahead. You know, the Ling sound test, it's a deceptively simple test. It looks like a very easy, straightforward test to present. However, there are some tricks to presenting it so that you get accurate information. So let's look at these tips on how to deliver the Ling sound test. Minimizing your background noise. Maybe that's my problem here. Maybe there's a bit too much background noise. We really want the sounds to stand out from the background noise so that you're getting a clear response. We want the delivery to be in a conversational volume, conversational voice with no lip reading cues. I remember once I was presenting on how to deliver the Ling sound test to a big group of participants who had never heard about the test before. So it was a new test. And then I got them up after I'd done the how to deliver the test to do some role play. And the first group came up and they said, well, this child's new to listening with their cochlear implant, so we're going to do the test using lip reading. And I realized I hadn't really explained the purpose of the test. The purpose of the test is to check what the child can hear using their hearing technology. So no lip reading for this test. For a beginning listener, you're going to start up close. And as they become more experienced and you want to learn more about what the technology is giving them over distance, you're going to deliver the sounds over distance, up to about 3 meters. Cochlear implants can even hear a bit further, maybe 4 or even 5 meters. The gold standard of the delivery of the Ling sound test is to not add suprasegmental information. What do I mean by that? Keeping each of the sounds the same length, the same sort of intensity, although we know that some of the sounds are going to be louder. R is a louder sound than S, for example, delivering it with the same amount of vocal force. And maintaining the pitch of each of the sounds, not adding in pitch changes to each of the sounds. Having said that, however, for beginning listeners, you will use suprasegmental cues to capture their auditory attention. For children in particular, you're going to mix up the order of the presentation of the sounds. This is to prevent children guessing about what the next sound is going to be if you're very consistent in the delivery of the sounds. You're going to vary the wait time between each sound so that children don't get into the pattern of expecting a sound at that same pause rate. As I said, it is a deceptively simple test, but we do see some common problems in the delivery of the test that does compromise the results, does compromise the information that you get from this test. If there's too much background noise when you're delivering the sounds, you will not see a clear response. If you don't leave enough silent wait time, if there's not that pause before the delivery of the sound, then the responses that you're seeing from the child or from the individual will be mixed up with responses to background noise. Maybe the child is too distracted at the time when you're delivering the sound. If you look at this picture here of this little person who's holding the dinosaur, that looks great. Maybe you want to give the child something to play with while you're delivering the sounds. This child clearly has got some tactile input from the toy, maybe also visual input. They're very attracted to this toy. That's going to be too distracting. They've got visual input, they've got tactile input. The addition of an auditory input might not be distinct enough. So we really want to minimize input at the time of the delivery of the sound. Maybe the speaker's mouth is visible. You know, I just gave that example about the clinician that was going to deliver the Ling sounds through lip reading. We don't want the mouth visible. In fact,